Hello, good afternoon everyone. How are you all doing? Thanks for coming. Thanks for coming to the Journal Club stream today, or maybe you're watching on YouTube afterwards. So thanks for dropping by. My name's Robert Palgrave. If we haven't met, let me introduce myself. First, I'm going to put on some music. Actually, let's put on a little bit of music to help things flow a little bit smoother. So my name's Robert Palgrave. I am a university professor. I'm a professor at University College London, UCL, which is quite a large university in the middle of London, which you may have heard of. So, what is this? Many of you, perhaps all of you, will be new to the channel. So I'll also, as well as introducing myself, tell you a little bit about the channel and what the idea of the channel is. So the Journal Club is a Twitch channel for discussing scientific papers. So many universities, many research groups, many researchers in industry or academia all over the world will be familiar with the idea of a journal club. So the idea of a journal club is that a group of scientists will meet, a group of researchers will meet, and they will discuss one or more recent papers, or maybe not so recent papers, one or more interesting papers that have come out in the literature that may be relevant to their research, or may just present some interesting new ideas. And they'll discuss anything about them. They'll discuss how they relate to their current work, broader issues around the science that those papers are presenting, what things they like about the papers, what things they don't like about the papers, what figures they like, what pictures they like, how terrible the colour schemes are. So all of those things and more are open for discussion in this journal club, in Twitch Journal Club. So every stream, and I've set up to do 3 streams a week. So we'll see how realistic that is. But every stream I'll be discussing at least one main paper, and I may bring in other papers or other resources as well to kind of help with the discussion of that paper. But it's mainly going to be around one paper. So we'll read through the paper, not word by word. I'm not going to go through every single part of it, but we'll have a look through different aspects, and I'll give my views. And if anyone shows up in the chat, then they can also give their views as well, and that would be excellent. And that's the entire point. It's supposed to be eventually an interactive process where you guys can get involved as well. So. How do I choose the papers? Well, my research is in inorganic chemistry, in materials chemistry, and material science. So that's the kind of papers that I'm going to be choosing, because they're the ones that I at least supposed to have some kind of background knowledge in. But who knows? As the channel progresses, there may be opportunities to expand that range of topics a little bit more broadly, and maybe look at some other areas of chemistry, other areas of physical science, other areas of science in general, or maybe even move away from science and look at some other kinds of journals. But that's for the future. For now, I'm really only qualified to talk about materialsy things, but there's a lot to discuss there. There's a lot of very interesting materials research going on all over the world, so we will not be short of papers even if we just stick to that topic, I don't think. So what about the paper for today? Well, the paper that I'm going to share with you, I'm actually going to put it up on screen now. So I think I tweeted this out. If you're not following us on Twitter, then you can do that. I think there should be links somewhere on the screen if you're watching on Twitch. There should be a link to the Twitter profile. The Twitter profile will tweet out the upcoming papers that will be discussed. So this is the one for today. So in choosing papers, I'm pretty much going to universally choose what's called open access papers. So that's basically papers that anyone in the world, as long as you have an internet connection, and seeing as you're watching me, I guess you do, anyone in the world can access. So I think by the miracles of modern technology, if you type in chat !paper, and I'm going to do that right now, and then press enter, then hopefully the chat bot will reply to you with the link to this paper, which is convenient if you guys want to read along as well. So this is a paper entitled The Mystery of Black TiO2 Titanium Dioxide, Insights from Combined Surface Science and In Situ Electrochemical Methods. So this was fairly recently published. It's back in 2021, so just last year. This is in this ACS Materials Gold, I think is the correct pronunciation for this journal here. ACS Materials Gold. I don't think you say ACS Materials Au. Maybe people do. Maybe some people do. But I think the preferred pronunciation is ACS Materials Gold. So gold here obviously refers to the element. It's also a play on words because this is a gold open access channel. So that means that all of the articles are free to access for anyone. It's published by the American Chemical Society. So have a look at the link in the chat. If you missed the link, then you can type !paper with no space, and the chatbot will reply to you with the link to the paper. So the mixture of black TiO2. So I'll have a little look at the abstract, then I'll tell you a bit about my reasons for choosing this paper. So titanium dioxide TiO2 is often employed as a light absorber, electron transport material, and catalyst in different energy and environmental applications. Yeah, absolutely. So TiO2 is kind of the prototypical photocatalyst. So it was probably, I think it was the first material identified as a photocatalyst. And a photocatalyst is something that absorbs light, and by absorbing that light, it's able to do some chemistry. So it's able to catalyze some kind of chemical reaction. So titanium dioxide was the first one of those developed. I think back in the 70s, it was actually used for photoelectrocatalysis. And this was seen as really important at the time, and it still kind of is, because TiO2 can be used to, one of the reactions that's really interesting for TiO2 photocatalysis is to split water. So to take water, divide it up into hydrogen and oxygen, and of course the hydrogen can then be used as a fuel. And if you can do that with sunlight, if you can do that by shining sunlight onto TiO2 as a photocatalyst, that could be a really effective way of generating renewable energy. So it's also used as electron transport material, so that's in things like solar cells. So solar cells, devices which absorb light, create electricity, electrical power, and they're often used as electron transporting materials in here. And a catalyst, well, I kind of mentioned that as photocatalyst as well, in different energy and environmental applications. Heat treatment in a hydrogen atmosphere generates black TiO2. So one thing I guess to know about TiO2, one of the most important characteristics is that it doesn't absorb any visible light at all normally. So it's normally, if you have it as a powder, it's completely white, a really bright white powder. In fact, it's used in lots of paints. It's actually a dye used in paints. It's actually a dye used in foodstuffs as well. TiO2 is edible, so you can use it in foodstuffs. So it's completely white, or if you have it as a thin layer instead of a powder, then it's colourless. It's completely transparent, like glass would be. But heat treatment in a hydrogen atmosphere generates black TiO2, which they call BTiO2, allowing better absorption of visible light, which places the material at the forefront of research. Yeah, that's kind of true. We'll look at some stats for that in a minute, but that's a fair statement, I would say. At the same time, hydrogen treatment also introduces trap states. We'll discuss that later on. And the question of whether these states are beneficial or harmful is rather controversial and depends strongly on the application. Fair enough. We employ combined surface science and in situ electrochemical methods to scrutinise the effect of these states on the photoelectrochemical PEC and electrocatalytic EC and charge storage properties of black titanium, TiO2. Lower photocurrents were recorded with increasing number of defect sites, but the electrocatalytic and charge storage properties improved. We also found that PEC, photoelectrochemical properties, can be enhanced by trap state passivation through lithium-ion intercalation in a two-step process. The passivation can only be achieved by utilising small-sized cations in the electrolyte, but not with bulky ones, tetrabutyl ammonium. This thing here is tetrabutyl ammonium. The presented insights will help to resolve some of the controversies in the literature and also provide rational trap state engineering strategies. Okay, so nice abstract there. I think they kind of clearly sell out what they want to do, but maybe even more so is, of course, the graphical abstract, which shows a nice little cartoon here. I think there's kind of some depressed looking electrons on the left, but after their lithium intercalation, the electrons are perked up a little bit. They're a little bit happier. Gives you an idea of what their they're aiming for in this paper. So a little bit of background on why I chose this paper, or why I chose a paper on black TiO2. So I think the original paper on black TiO2 came out in 2011, so over 10 years ago now. And it really has taken off, I would say. So the original paper I think came out in Science. In fact, I have the original paper somewhere here. I think this is it. No, that's the wrong one. This is the original paper, yeah. So this original paper from Chen et al. Published in February 2021 in the journal Science, very famous journal. And it's entitled Increasing Solar Absorption for Photocatalysis with Black Hydrogenated TiO2 Nanocrystals. So this paper really caught people's imagination. I think it's got about 5,000 citations at the moment after 10 years, which is quite a lot. And even at the time, titanium dioxide and titanium dioxide photocatalysis was a really kind of actively researched area, really important area. Maybe even going back to this earlier Science paper from 2001, so another 10 years before that, so going back just over 20 years now, to this paper, visible light photocatalysis in nitrogen doped TiO2. So this paper is even more, as you may expect because it's older, got even more citations than the previous one. It's over 10,000 citations now. So nitrogen doping TiO2, and indeed this hydrogenation of TiO2, which was in the 2011 paper, are really solving one of the big problems with TiO2 photocatalysis. And the big problem of TiO2 photocatalysis is that titanium dioxide itself doesn't absorb visible light, so it only works with ultraviolet light. So even though it has this really excellent catalytic activity, great potential for doing chemical reactions like water splitting to generate renewable energy, or even loads of other different chemistry, even driving other kinds of chemistry on the surface of TiO2, this only happens in ultraviolet light. So if you want to use sunlight to split water into hydrogen and oxygen, TiO2 will give you very low efficiency because it's only a very small part of the sunlight, the ultraviolet portion of the solar spectrum, that can actually be used to drive that chemistry, to do the water splitting. So all the way back since 2001 in this original, or this very famous paper on nitrogen doping TiO2, the reason this paper was of such interest was because here they managed to report a way to make titanium dioxide visible light active. So they managed to dope TiO2, so they add in an extra element, in this case nitrogen, and that element was able to change the way that TiO2 absorbs light, and it's able to make it absorb visible light. I think they maybe have some photos. They don't even have photos in this paper as well, but they do have an absorption spectrum. So they have an absorption spectrum down here. And you can see, yeah, so this one on the right here I think is what we want to be looking at. So you can see the kind of original TiO2 material was this one here, and then after you dope it with nitrogen, let's change the colour, after you dope it with nitrogen, then you get all of this extra absorption here in the visible region. So you're dramatically increasing. So this is the visible region here. If you look at the wavelength, 400, 500. 400 is kind of the bluest blue light. 500, 600. This is the kind of green going down into red light here. So your TiO2 nitrogen doped TiO2 is absorbing that light in the visible region, and as they showed here in this paper, it's actually able to do photocatalysis with that. So under UV light, the photocatalysis is better. They're measuring the photocatalysis by how much CO2 they're producing when they're destroying an organic pollutant, I think. So UV light is most effective, but the nitrogen doped TiO2 is pretty effective in visible light. You get quite a lot of activity compared to the undoped TiO2, which doesn't really do anything in visible light. Okay, so they showed really nicely that the nitrogen can be incorporated into TiO2, and it can also not only be incorporated, but it can also cause visible light photoactivity as well. So that's a nice finding. So that was a major paper, and so many people jumped onto the bandwagon doping things into TiO2 in order to increase the photocatalytic activity. I may have been one of those people. If you have a look at a few previous papers, there's some on nitrogen doping TiO2, and there's a lot to unpack there, and I won't try and do that now, but there's a huge number of papers on nitrogen and other kinds of doping of TiO2, sulfur and phosphorus, all sorts of other things. Basically any element you can get your hands on, people are trying to dope it into TiO2 with various levels of success. But you may have noticed 20 years on, we're not living in a world powered by hydrogen from nitrogen doped TiO2 water splitting, sadly. In fact, we're still living in a fossil fuel power world, and we know the problems that's causing us, especially at the moment with various things going on around the world. So turns out this wasn't the answer to really effective water splitting. There's a huge amount of literature to go through if you want to understand why that is. But anyway, that's a little bit of background. So interest in making visible light active TiO2 has been around for a long time. So that kind of explains, I guess, some of the interest around this black TiO2, because, you know, turning TiO2 from something that's completely colorless, doesn't absorb any visible light at all, to something black that's absorbing, you know, most or not, if not all of the visible light that's incident on it, is quite a big change. So how did they do this? Well, there's a clue in the title. They hydrogenated, so they reacted it with hydrogen, and in fact I can't remember where here it is down here, I even highlighted it. The experimental method was quite extreme, so they used 20 atmospheric pressure, so 20 times atmospheric pressure of hydrogen at 200 degrees. They put their TiO2 powder in there and cooked it under huge pressure of hydrogen for 5 days at 200 degrees, and what they ended up with was this black material here. So here you can see on the left, this is normal TiO2. No, you can't see anything because I haven't scrolled up enough. Sorry. This is normal TiO2 on the left here. On the right here, you can see the black TiO2 after hydrogenation, and as the name suggests, it's black. But most of the characterization that they did of this material seemed to show that it was fundamentally the same material. So if they look at the X-ray diffraction here, which tells you about the crystal structure, it looks pretty much the same before and after. The peaks are very broad. That shows they've got nanoparticles, and that's indeed what they started with. Started with nanoparticles of TiO2, and still are nanoparticles afterwards. The peaks are pretty much as broad. If you look at the Raman, so the Raman peaks here, you can see there's a few additional peaks here. I think it's difficult to understand what they are, but the main peaks are still present of TiO2. So Raman tells you about the vibrational properties, can be used to identify what material you have. And so, you know, the vibrational properties, there are some differences, but they're largely unchanged. They looked at some microscopy here, and so you can actually see with a transmission electron microscope here, you can actually see the nanoparticle. So this is the nanoparticle here. The little dots inside, these little dots, these are the atoms. These are the atoms in a nanoparticle. So TEM is an amazing technique, really. It really lets you kind of zoom in pretty much as far as you can zoom in. You don't get much higher resolution than seeing the individual atoms. Of course, what we're really seeing here is a column of atoms going down rather than just one atom. But you can see afterwards, and this is kind of what they claim here, after the hydrogenation, you still have this kind of core. The middle of the particle still has this very kind of regular structure. I should say the reason these dots are all lined up in an order is because this material is crystalline. So it's a highly crystalline material, which you can see the arrangement of atoms is very orderly there. And indeed, in the middle of this particle after hydrogenation, you also have an orderly arrangement of atoms. So you still have a crystalline center, but around the outside, this is their claim here, around the outside, you have part of the particle which is not ordered. So the atoms aren't forming a very regimented, irregular structure here. They're kind of much more disordered. They're more randomly arranged. And they're saying that this is the outer layer of the TiO2 has been disrupted. The crystal structure has been disrupted by the the hydrogenation process. So this is their kind of cartoon of that, and this is what they see inside as well. So they did some photocatalysis, and they showed that the photocatalysis, now they're looking at the degradation of an organic pollutant, so we want this to go down fast now to show quick degradation. The degradation is very fast compared with white TiO2. Black TiO2 degrades much faster. Note, white TiO2 is still doing something, so I think that what that tells us is that the light that they're irradiating this experiment with when they're doing the photocatalysis must have some UV component there, otherwise the white TiO2, the undoped TiO2, would do nothing at all. You just expect to see a straight line across the top. But the fact it goes down means there must be some UV there, but it's clear that the black TiO2 is kind of doing a better job, and they didn't just do this once, they repeated it many times, and you can see that they also generated hydrogen using the same method. So this is the kind of background to, I will just show you at the end a bit of characterization they did. They did a little bit of density functional theory, so they did some calculations on the material. I guess they just kind of plonked in the hydrogen where they think they might go, and they came up with this density of states here, which tells you about the energies of the electrons within the material, and compared that to the bulk TiO2 without any dopant, and you can see they have these extra features inside the band gap, which they can attribute some of the enhanced properties to. But what I was going to look at was some more experimental stuff up here. So we have some photoemission spectroscopy here, and this valence band XPS especially, is a measure of the outermost electrons, so it's similar to the DFT method that we showed before. One thing that really struck me about this, looking back 10 years, this is 2011, so 11 years now, just how noisy the valence band spectra are. So valence band spectra in XPS, which is X-ray photoemission spectroscopy, the intensity is low compared to other peaks. So this is another peak you might see in XPS. This is a peak coming from oxygen. This peak is much more intense than the valence band, but these days with modern equipment, even 10 years on from what we see here, it's much easier to record high, much less noisy, high signal to noise ratio valence bands, much easier. So you can get much smoother spectra here. So it was kind of interesting to see just how noisy this was, published in a top journal just kind of 10-11 years ago. Anyway, they showed some important differences here. So experimentally you can see a difference in this spectrum, and they interpret here with this cartoon as a change in the distribution of energy levels, distribution of electrons in the outermost electrons in the valence band region of this material, which kind of makes sense, and it ties in with their DFT, their calculations as well. So that's a little bit of the background. This is the origin story, I guess, of black hydrogenated titanium dioxide nanocrystals. This paper is, as I said, many thousands of times cited, and a lot of people since then have really piled onto this. And there's if you do a Web of Science search for black titanium dioxide, you get almost 1,000 papers, I think. So there's a lot of work to do there. So fast forward about 10 years, and we get to the paper that we're discussing today, which is this one, which is the mystery of black TiO2, insights from combined surface science and in situ electrochemical methods. So, as I said, the reason that I'm interested in this is because those 10 years ago when that first paper came out, I remember looking at that paper when we were discussing it in a journal club, perhaps not dissimilar to this one, except it wasn't on Twitch, because Twitch wasn't invented at that stage, if you can imagine such a world. But we discussed that original black TiO2 paper, and we thought, I was working as a postdoc in a different university at that point, and we thought, should we be looking into this? Should we be looking at black TiO2? Is black TiO2 the future? I think the decision we made looking at that paper was that probably it wasn't the future. I think we decided, based on some things we read about the photocatalytic results, we thought that it wasn't maybe that that interesting. It wasn't going to be that big. Well, I don't know. You can judge, I guess, whether we were wrong in that, because like I said, there's at least 1,000 black TiO2 papers since then, investigating all sorts of things. But I would say, even 10 years on, the situation is not by any means clear cut with this material. What this material is, how this material works, are very much open questions as far as I know in this field. So I haven't really been working strongly in the TiO2 field for a long time. So the reason that I chose this paper is because I saw this paper talking about the mystery of black TiO2, and I really wanted just to see what had happened since that original paper 10 years ago, when myself and a few colleagues decided that there wasn't any feature in black TiO2. I really wanted to see what was going on there. So before we get into this paper proper, just a couple of other ones to mention. There was a nice review article back from 2015 on this, black titanium dioxide nanomaterials. I think this is the original author. Is this the original author? Let me see. Is this the original author? It is the original author. Yeah, I thought it was. So from the original authors of the black TiO2 paper, this is a nice review article, which I'm not going to go through, but it actually highlights a lot of the issues in black TiO2, in the science involved in this. So this is an open access, I'm afraid. If you do have access to it and you're interested in black TiO2, definitely worth checking out. I think a really nice paper. Some of the things they highlight are actually going to be really relevant in the paper that we look at. So maybe we should just get on with doing that. Maybe we should just get on with that. So this is the paper we're looking at. If you want to find this paper, you can type !paper in the chat, and you'll be rewarded for your efforts with a link. It is open access. Anyone in the world can access this. I already read out the abstract a little bit earlier, so sorry if you missed that, but you can read it for yourself. It's a paper studying TiO2, black TiO2, and claiming, at least from the title, that it's going to solve the mystery. Maybe it doesn't claim it's going to solve the mystery, but there's a bit of an implication there that the mystery is going to be solved, which is maybe what clickbait attracted me to this paper in the first place. So maybe there's a lesson there. If you put some clickbait titles, you're more likely to end up on this Twitch stream. You may think that is a bad thing, who knows. Anyway, so the introduction, I've kind of talked a little bit about this already, so I might not go through this in too much detail. I've talked a lot about TiO2, what it does as a photocatalyst, as an electron transport layer in solar cells, as a pigment in paint or in food. You've probably eaten, you may well have eaten TiO2 today. It's highly likely actually that you've consumed some today. Probably not black TiO2, but it's probably not that poisonous, but hopefully not, because it probably hasn't been approved for human consumption. But you've probably eaten some normal TiO2 today, so I won't go through in too much detail the introduction, because they highlight a lot of the same points that I have. But maybe this part here is worth highlighting, that the black TiO2 colours result with increased light absorption in the visible and near-infrared regime. Maybe I would say region. There are examples of literature where photocatalytic PEC activity of TiO2 were enhanced by this procedure. Absolutely. So I think the way they worded that is interesting. There are examples. There are examples in literature where it does that. I think there's also a lot of examples where people make black TiO2 and it doesn't perform better than other things. So that's actually one of the big problems, I think, in the area of black TiO2, is that I don't think we really have a good answer to the question, what is black TiO2? What is this material? I think probably the different materials, and this is highlighted in that review I mentioned a minute ago, the different materials that different people are making may well be quite different. So there's different hydrogenation procedures, there's different starting materials. Remember, these are nanomaterials, so there may be different particle sizes, different crystal phases, different surface chemistries, and then modified by different kinds of hydrogenation procedures to lead to potentially quite a wide range of different materials. And I think that is one of the problems in this field. That there's a lot of different black TiO2 materials. Actually, this applies to a lot of materials chemistry. This idea, but there's a lot of different black TiO2 materials, and so that makes understanding their properties a lot harder, because if one group's black TiO2 does a certain thing and another group's black TiO2 does something completely different, you know, how do we make progress there? How do we kind of progress and understand kind of the fundamentals about what's going on? But anyway, there are examples, is a nice way to put that. There are examples where the activity is enhanced. I think there's also examples where it's not enhanced. Okay, and there's some different reasons for that. So increased light absorption, improved charge carrier separation. So that's when you absorb light, when a semiconductor absorbs light, it creates an electron and a hole. So it creates a free electron and free hole, or at least it can do. And these are charge carriers. So if these electrons and this missing electron or a hole can travel through the material, then they can transport charge, and so they're called charge carriers. So one important step for photocatalysis or photoelectrocatalysis or even electrocatalysis is separation of these charge carriers, separations of electrons and holes. If they don't separate well, then they can recombine with each other, so that deactivates the material. Decreased resistance in charge transport in the bulk, so you could call that increased mobility of the charge carriers, and enhanced charge transfer at the semiconductor electrolyte interface, and suppress recombination. Okay, so quite a range of things there that hydrogenation may be doing. So increased light absorption gets more light into the material, creates more electrons and holes. Improved carrier separation will make them separate from each other and live longer. Decreased resistance to charge transport, so increased mobility of those charge carriers allows them to move through the material better. Enhanced charge transfer at the semiconductor electrolyte interface allows those charge carriers to move from TiO2 onto whatever is absorbed on the surface. So whether that's water, if you want to split water, your electron has to go onto the water molecule in order to produce hydrogen. So enhanced charge transfer at the surface, or suppress recombination, so that's kind of the same as improved separation, I think. It just means that the recombination between the electrons and holes is slower, so recombination of electrons and holes is a deactivating process in these kinds of catalysts. So slowing that, suppressing that process is beneficial for your catalysis. Okay, so an interesting observation was that the photocurrent enhancement is mainly caused by improved photoactivity in the UV region. Okay, that's pretty interesting. So even though this thing is absorbing visible light, and actually this is a point that I think we were discussing kind of in that meeting 10 years ago. The photocurrent enhancement, or even the photocatalytic enhancement, is mainly caused by improved UV light photoactivity as opposed to visible light photoactivity. So the fact that you've made black TiO2, you may think, well, the reason it's working well under certain illumination, under sunlight maybe, is that we're absorbing the visible light, and that visible light is then going on to do some chemistry, some catalysis. Actually, it may well be that you're just made the visible light absorption is kind of a distraction, and it's the UV light that becomes more efficient. So it makes more efficient use of the UV light. So it may be not actually using the visible light at all, it's using the UV light more efficiently. So that's why you end up with a better activity. And yeah, they kind of continue that point here, where they talk about the contribution of visible light to production of charge carriers can actually be negligible in terms of producing photocurrent. So skipping over a few little bits, maybe we should talk about what they did here. Yeah, maybe we'll just sum up there. There's a few other points about the different effects of defects, or the different effects of hydrogenation. These examples indicate that the effect of defects is controversial, and a better understanding of structural and electronic changes that occur during hydrogen treatment is necessary. Yeah, absolutely. So even 10 years on from the initial report, I think it's pretty fair to say, at least, saying it in slightly less diplomatic language than they've used here, people don't really know what this stuff is or why it works. They don't really understand what the defects are. They don't understand the structural or electronic changes that occur during the hydrogen treatment. And if you don't understand that, it's difficult to then understand why this material works. Why is it better material than just white TiO2, than regular TiO2? There's good evidence to show that hydrogenation can cause improvements, but why does it do that? Okay, according to certain transmission electron microscopy measurements, which we just saw, I just showed you a little bit a minute ago, the enhanced catalytic properties of black TiO2 are caused by 1 to 2 nanometer thick disordered TiO2 surface shell surrounding a perfectly crystalline core. Okay, so if we go back to the original paper that I showed you a second ago, these are one such TEM image. So here you have your crystalline core, here you have your kind of amorphous or poorly crystalline layer kind of around that. Right, back to here anyway. Most explanations for the narrow band gap with black TiO2 rely on the synergistic action between the oxygen vacancies and structural defects of non-specific origin. However, the proposed outermost Ti2O3 is another semiconductor with very narrow band gap, which might explain the phenomenon. Yeah, absolutely. So Ti2O3 is a different kind of titanium oxide. It's titanium 3+, as opposed to TiO2, which is titanium 4+. And because titanium 3+ has got one electron in its outer shell, it's a D1 metal, as opposed to TiO2, which is a D0 oxide, so it's D1 oxide as opposed to D0 oxide. It behaves very differently especially its interaction with light. So that one electron in a d orbital can easily be moved around. In fact, it's in a d band, so it kind of behaves more like a metal, with a very, very narrow band gap here of 0.1 electron volts. 0.1 electron volts. So it could be this Ti2O3 region is the cause of the black colour. This material is a stoichiometric compound. Okay, this is what I just said. Contains Ti3+ in more stable form than oxygen deficient TiO2. Okay, stability is always kind of debatable, but you could always ask under what conditions. The problem with this interpretation is that in most cases the detection of Ti3+ in black TiO2 is very difficult, which is surprising if the outermost layer contains only this oxidation state. These contradictions are summarised in table S1. It's actually quite a nice table. Maybe we'll quickly look at that. If I have that, so this is a supplementary information. Let's maybe need to zoom out from here a little bit. Zoom out a little bit, and table S1 I think is the table of contradictions. Observations gathered from literature and their possible explanations. So I'm not going to go through all of these, but I think this is a nice approach actually they've taken this paper to show that there are even after 10 years there's a lot of unresolved questions about black TiO2, and they mention some of these things here. So for example, the point we were just talking about, the outermost layer of black TiO2 consists of a disordered TiO2O3 shell. If it does, it's hard to explain why we can't see, or why we often don't see titanium 3+ in the material. We'll talk about the way we might detect titanium 3+ later on. Okay, back to the main paper. So the rest of the introduction I think covers points that we make, but let's get on to the most important part of the introduction, which is where they tell us what they're actually doing in this paper. So in this paper we present insights on the optoelectronic features of different nanoparticulate TiO2 electrodes deduced from in situ spectroelectrochemical methods and photoelectrochemical measurements. These results are complemented with X-ray and UV photoelectron spectroscopy, which is one of our favourite techniques here on the Journal Club. Based on these results, we analyse the influence of trap states on a PEC, photoelectrochemical, electrocatalytic and charge storage properties. Finally, we describe how to improve PEC properties by passivating the defect states with incorporation of lithium plus ions, which I think is kind of a new idea there. So that's their kind of statement of intent, really. That's what they hope to do in this paper. So we're gonna have a little look through. It might be worth, I think, the experimentals at the end. I always quite like to look at the experimental to see how they make their stuff. Yeah, let's have a look at how they So often, for reasons that don't really make any sense to me, experimental section you'll find at the end of the paper. So I'm going to scoot right to the end because I quite like, in our research we quite like making things, so I'm always interested in how they made the stuff. I think that's pretty important to know actually before you start reading the results. How do they make the stuff? So the preparation of spray coated suspension, air oxide P25 TiO2. Okay, so P25 is a very famous kind of brand, I think it's a brand name, of TiO2 which you can buy commercially from this company called Evonik. And P25 is really a really widely used material. It's a mixture of two different crystal structures of TiO2. It's got that anatase rutile in there. I think it's majority anatase. And this is a kind of gold standard photocatalyst that's used, for comparison. Anytime anyone wants to make a better photocatalyst, they compare it with P25 to see whether it's better or worse. So kind of the gold standard of catalyst comparisons, especially for TiO2. P25 is a nanomaterial, so it's nanoparticles of TiO2. I think the 25 is to do with the size, if I remember right. So I think it's about 25 nanometer particles. So pretty small particles of TiO2, very high surface area. So that gives you high kind of absolute catalytic activity, which is, some of the attractive parts of that material. Also, the fact it's mixed phase, anatase and rutile, is pretty important as well. I think there's a lot of papers about the kind of synergistic relationship between anatase and rutile for photocatalysis. So the idea that you have both of these catalysts or both of these phases there at the same time, I think is thought to be at least very important for P25's activity. Anyway, so they took basically the best photocatalyst you can have, or best undoped photocatalyst you can have. They dispersed it in ethanol. Fair enough. FTO is fluorine doped tin oxide. So that's they talk about now a layer. So FTO covered glass. This is a conducting layer. So they need a conducting layer because they're doing electrochemistry. So they need to deposit their P25 on a conducting layer. So they took some FTO coated glass, so conducting glass basically. They cleaned it a certain way. Blah 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 blah. Preparation of TiO2 layers. So the FTO coated glass substrates were sonicated in acetone, propanol, deionized water for 5 to 5 minutes. Oh, there's a range of minutes there. Between 5 and 5 minutes prior to use. The P25 TiO2 nanoparticles were spray coated onto preheated substrates at 140 degrees from an ethanol-based suspension. Okay, so they kind of mixed up their P25 with ethanol, and they just took a spray coater and sprayed it on to the hot substrate. Don't get it too hot or you're going to set fire to your ethanol, depending on what atmosphere you do it in, if you do it in there. But by doing that, they coat an evenish coating of these nanoparticles onto the FTO layer. During the spray coating process, the electrodes were masked to have an exposed geometrical area of 1 centimeter square. The same loading is achieved by using the same number of spray coating cycles. Okay, so they put 18 micrograms per cyclone. They did that 60 times. After the spray coating process, the electrodes are heat treated in a tube furnace at 400 at 2 hours in air, argon, or hydrogen atmosphere. Okay, is it pure hydrogen? They don't mention whether it's pure hydrogen or not. But this is their methodology. Now, if you've been here since the beginning of the stream, or watching since the beginning of the video, you'll remember back in the original paper here, they used quite a different method to produce their black TiO2. So they used 20 bar of hydrogen, so that's 20 atmospheres. So I think the most of those guys in the current paper we're looking at were using was one bar. They just say in a hydrogen atmosphere. I'm guessing they just use a kind of normal pressure there. But these guys use 20 bar, and they did it for 200 degrees for 5 days. Whereas here we have 400 degrees for 2 hours in a hydrogen. So lots of differences there already. Not only the fact that this is a thin film as well. So we have a thin film. In this paper they're using a thin film. In the previous paper they were using, they were just using a powder. They were just using a powder of this stuff, look like this. So the white powder going to the black powder. So a lot of differences there in how they make the material. Characterization I'm not going to really go over unless anything becomes kind of important later on. So let's go back up to their results and see what they're telling us about these materials. There's a lot in here to unpack. We may not get through everything through this stream, but we'll have a look at some of the results and I'll point out maybe some things which are interesting. So the P25 nanoparticles are spray coated on TFTO and annealed in air, argon or hydrogen atmosphere in a tube furnace. They just told us that already. After the heat treatment, the colour of the electrodes changed instead of figure 1. So just in terms of the colour, we have pretty much a similar change, at least from white to black, that we saw on the 2011 paper. So annealing, heating up under hydrogen, causes this colour change from white to black. And they're showing us well, they're not actually showing us the absorption spectrum, which is kind of a shame. Maybe they couldn't get an absorption spectrum. In fact, let's see how they recorded this this spectrum here. So what they're doing here is what's called a talc plot. So this is a talc plot, which is a method to determine the band gap of a semiconductor. So this weird kind of unit they're using here is just something that comes out of the different ways you can do a talc plot. So a talc plot is you take an absorption spectrum, a visible light absorption or a UV visible light absorption spectrum, you process it in a certain way, and this is one of the ways you can process it, and that will give you a plot which tells you about which you can extrapolate with a straight line. You can see these little dotted lines here. You extrapolate down to give you a band gap. Now, there's lots of issues with doing this. One of them is exactly how you define this straight line region. So they haven't shown us the entire spectrum, which might have been nice to see a little bit more up here. What goes on? They kind of cut these spectra off. You can kind of see. It might have been nice to see what happened here. Did it go kind of like this, or did it one of them go up like this, or how did that work there? That way we'd be able to judge a little bit better, I think, how they selected this straight line portion, because you can see, I mean, especially on this blue one, the straight line portion doesn't even really look that straight in the region that we are seeing here. It's kind of curved. So I would have liked to see a little bit more there. But also, I would have liked to see, I think, just the absorption spectrum on its own. I don't think they show that anywhere. Maybe I'm being a bit mean to them. Maybe they show it in the supporting information, which we'll quickly look in, but I don't actually think they do. Oh, they do. They do. Let me scroll down. I apologise to the authors. They do show it in figure S1. So the absorption spectra here. There's not a huge difference between them, is there? I mean, clearly the black TiO2 here. Clearly the black TiO2 is absorbing slightly more in a visible region, slightly more than what they call a grey TiO2 or the white TiO2 here. So they have caused some difference, some measurable difference in there with their hydrogenation. You've got to think what other factors could be at play here. So an important consideration, their electrode is made of these nanoparticles, these really, really small particles. So nanoparticles are very scatter visible light very effectively because they're kind of the same size. They're pretty much the same wavelength as visible light, so they can scatter it very effectively. So that means the scattering of the light, I think, is going to be pretty important in the absorption spectrum they measure, depending on exactly how they measure it. So I wonder how much this change in the absorption spectrum could actually be due to a change in something to do with the nanoparticulate structure of their materials. So have the nanoparticles changed size? Have you got larger? Have they got smaller even? How might this affect the scattering of light? These kind of things might be important as well. But just looking kind of optically, just looking at the picture, definitely looks like you've got a darker color here. What they call grey TiO2, visually looks different as well. But they give us so they tell us that they have this. Let's choose a different color just for no reason. They tell us that they have this UV absorption in figure S1, which we just looked at. Still, I don't know whether they recorded that as a transmission spectrum or as a reflectance spectrum. I don't think they say that. Maybe it's down below in experimental, but probably not too important. Anyway, the electronic transition from valence band to conduction band okay, this is the absorption edge here. The W and G TiO2 samples, so the white and the grey ones, showed small absorption in the visible region, which is likely caused by light scattering off the layers. That's just kind of what I just said. Compared to the black TiO2, it showed an increased visible light absorption, slightly, only a little bit more, but yeah, a little bit more, associated with the transmission of the valence band to different mid-gap states, such as titanium 3+ state, i.e. oxygen vacancies. Okay, well, identification of Ti3+ with oxygen vacancies, I mean, it's not literally the same thing, but I kind of get what they mean. The white TiO2 also contains certain amounts of these states discussed later. However, this does not seem to have a marked influence on the absorption characteristics of the white TiO2, maybe. There are examples in literature where the absorption features also appear in a near-infrared region attributed to the excitation from the Ti3+ levels to the CB, to the conduction band. Okay, so they're talking about, let's see if they have a cartoon later on. I think they do. I'm going to scroll down a little bit to find it. Yeah, so they're talking about these electronic transitions, which are the cause of visible light absorption. So visible light, almost all the visible light absorption that happens in materials, a large amount of visible light absorption that happens in materials is due to electronic transitions. So here they talk about moving electrons from the valence band, which are the outermost electrons of the material, into the conduction band, which are the next available energy level for these materials. And they're saying that this is the cause of the large absorption edge in the absorption spectrum that we see, and what they calculate the band gap from that edge. But they're saying that in the black TiO2 we have these additional absorption features which correspond to absorption from the valence band to some defect state, so some Ti3+ state or some other kind of defect state that may exist in the material, which they're going to try to kind of elucidate as they do their work here. Right, so back up to the introduction, the result. So the indirect band gap values, so that's the band gap values they've obtained from this talc plot here. These extrapolating these lines down. So they've used an indirect band gap calculation method, which again you might argue whether that's the most appropriate thing to do. So TiO2 rutile I think is certainly a direct semiconductor, direct band semiconductor. Anatase I think is almost direct. I think there's a very slightly low energy indirect transition. But anyway, they came up with these values of 3.25 electron volts, for white TiO2, 3.2 electron volts, for grey TiO2, which is kind of normal for anatase. P25 is largely anatase phase, and black TiO2 is 3 electron volts, so it's a little bit smaller. Again, I think it depends exactly how you do this linear extrapolation. I think looking at the if you extrapolate this absorption edge down here, if you took this part of the spectrum, I think you would expect very, very similar numbers from these three. So it's difficult to determine exactly. Sorry, this part of the absorption spectrum here. I was drawing on the wrong screen. Sorry. Let me draw. Let me choose a yellow colour for this. So yeah, if you took this part of the absorption spectrum, I think you would. It's a terrible drawing. I think you would get very similar band gap values for all of those samples. But it's difficult to decide rigorously sometimes where this talc plot should be taken from. So there's a little bit of uncertainty there. Anyhow, okay, let's go back to the main paper. So the first thing they do is do XPS. So XPS is X-ray photoelectron spectroscopy. So XPS was carried out to evaluate the chemical composition of the surface of the 3 different treated TiO2 samples. The survey scan showed identical chemical species at the surface of the samples. Let's go take a look. So they don't. Okay, right on the screen here. So this is the survey scan that they are talking about. So the survey scan contains different peaks corresponding to different elements. So they've labelled them handily for us here. So the main ones are interested in the titanium 2P. So of course you have titanium TiO2, the main metal, the main non-oxygen atom is going to be titanium here. We also have some carbon here, interesting. So the carbon comes from just contamination on the surface. So XPS is a very surface sensitive technique. So the surface contains a lot of carbon normally just from being out in the atmosphere, and you can see that carbon here. And of course the oxygen peak here. There's other peaks that arise from titanium. It's an oxygen OJ line here, titanium 3s. So just broadly speaking, there aren't any extra elements that have appeared during the treatment process, either the white or the grey, the grey or the black, which makes sense. You wouldn't really expect any extra elements to come in there when you just heat it up in hydrogen. One thing I should say, XPS can't really detect hydrogen, so we're not able to see hydrogen. There may be a lot of hydrogen in the black TiO2, but we won't be able to detect that in our using that technique. So they also do the look at the high resolution titanium 2P spectra. We're jumping back again to the supporting information, but for XPS it is worth it. It is worth it for XPS. Just put it in the main paper. Everyone loves XPS. It should be in the main paper. You shouldn't have to scrabble around in the supporting information to find it. But here we are, figure S3, high resolution XPS spectra of the Ti2P, oxygen 1s, carbon 1s, regions of the white, grey and black TiO2. So here's the titanium. Let's see if I can zoom in vaguely effectively on here. Let's see if this will work. There we go. So here is the titanium 2P region of this spectrum. Oh, our music is finished. Let's have some other music. The titanium 2P region of the spectrum here, and yeah, as they say, basically the spectra look pretty similar. So you have these two peaks. This is called a spin orbit doublet. You always expect this with titanium 2P because it's it's a p orbital which has a angular momentum of its own. So you can couple with the spin of the electron to give these two peaks. So the spectra kind of look the same. I mean, this one's smaller. I don't know why they maybe haven't normalized them. I don't think that's significant. There is I think a shift. I think there's a shift in the position of the peaks, which they'll talk about a little bit in the paper. But what they don't see, the main point that they don't see, is a big extra peak in the black TiO2, so the top one, which will correspond to titanium 3+. So if you had a mixture of titanium 3+ and 4+, you'd expect to see another environment for the titanium, another peak down here for the 3+ environment. But you don't see that, or at least they're not showing it. It's not very obvious here. So that's kind of interesting for the points for the reasons they described earlier. That one of the hypotheses is that you make Ti2O3, titanium 3+, on the surface, but you're not detecting it. So oxygen 1s, they've fitted this with a lattice oxide and a surface hydroxide, and again they don't look massively different in each of those cases. And the carbon peaks, again, this is a pretty typical carbon spectrum from just contamination from surface carbon that you get on the surface of these things. Again, doesn't really look like it's changed much. I'm kind of surprised that at 400 degrees treated in air, they didn't burn off some of that surface carbon, unless of course it's contaminated after the annealing process. Actually, that's probably more likely, isn't it? It's probably contaminated after the annealing process. Right, let me zoom out a little bit to get a better view here. That's the wrong paper. Here we go, back in the original paper again. So yeah, they showed the Ti2P spectra. This corresponds well to the binding energy of titanium 4+ in Ti2 materials, and they're listing the binding energy. 2 decimal places, probably a little bit overkill on the binding energy accuracy there. And with a peak separation, they talk about the spin orbit peak there. The presence of Ti3 was not observed for any of the samples, as I just mentioned. The determined binding energy of the titanium 4 was similar in the case of W and G samples, the white and the grey, but in the case of black, a significant shift was observed towards higher binding energies. This alteration in the peak position can be assigned to structural distortions on the surface of the black TiO2, as discussed later, I think. Maybe that's why. Difficult to tell just from the XPS alone, but I guess structural distortions could cause a change in the peak position. There's lots of other things that could cause a change in peak position as well. Maybe one of those very important for a semiconductor, especially a semiconductor you're doping, which is what they're doing here, is changing the Fermi level in the semiconductor. So doping, if you're doping electrons or doping holes, so if you change the kind of carrier concentration or change the electron richness of the material, let's say, rather than carrier concentration, is probably a better way to say it, you can either raise or lower the Fermi level in your material. So when you raise or lower the Fermi level, not many people realize this, or many people don't realize this, I should say, you move the peak positions in your XPS, because XPS, the binding energy scale, is referenced to the Fermi level. So when you change your Fermi level, you change your reference point, and so you change all of the binding energies. It's not inconceivable that by doping with hydrogen, they are changing the Fermi level and this might cause the change in peak position. I don't know, but it's something that maybe they could consider. And I think they see an increase in the binding energy of the titanium peak. That will correspond to putting more electrons into the material, to electron doping the material. And again, that's not impossible that hydrogen is doing that. In various different ways hydrogen could go in. You could definitely be adding electrons in, and so that could correspond with the shift in titanium peaks that we see. Anyway, they discuss that later. The oxygen 1s resolved region was also very similar for all samples, and I mentioned that. To observe, so they talk about the presence of hydroxide groups as they mentioned in the supporting information. To evaluate the effect of heat treatment in different atmospheres on crystallinity, XRD measurements were carried out. Rietveld refinement identified annotator and rutile phases in a 3:1 ratio in all cases, which agrees with the composition of P25 TiO2. Well, that's lucky, isn't it? So they measured the XRD, it tells you about the crystal structure. They got a pattern, an XRD pattern, which contained peaks from the rutile and the anatase, and they used this method of Rietveld refinement to build a model of a certain amount of anatase, a certain amount of rutile, and then they changed their model until it matched up well with the observed experimental XRD pattern. Rietveld refinement, very, very powerful technique for quantitatively analysing powder XRD. Really, really universally used in materials science, materials chemistry, and an example here, you can use it to understand phase fractions, which I've done, and they got a not particularly surprising result, which was a 3:1 ratio, which I think is probably what it said on the side of the bottle of P25, but it's always good to confirm that. So the heat treatment had negligible, if any, effect on the chemical composition of the films. Maybe they mean kind of structural composition, maybe they mean the phase composition, I would say, in line with other reports. So yeah, if you heat up anatase TiO2, it will eventually change into rutile TiO2. So that's a nice experiment you can do. If you have some anatase TiO2, you can heat it up to progressively higher temperatures, measure the XRD pattern, and eventually you'll see the anatase kind of start to decrease and the rutile start to increase. You can model that. It's a nice exercise to do to model the phase conversion of anatase to rutile, monitored by powder XRD. Is a nice way to do it. Right, the signals that either had one limited conversion. This signals that either limited conversion of the suboxide phase occurred and less than 1% Ti3 plus formed on the surface, i.e. below the detection limit of XPS. Okay, I think this section really belongs kind of here, because now they're talking about XPS again. Anyway, or a defective disordered surface was obtained with a stoichiometric composition. Yeah, this is definitely not talking about the XRD. This is talking about the XPS. The XRD doesn't really tell you about the surface. It's a bulk technique. So I think maybe they just kind of got these parts in the wrong order. To reveal the subsurface composition, argon bombardment was carried out to etch the surface of white and black TiO2 samples. So they're talking about XPS. So one thing you can do in XPS, you can use argon ion bombardment to sputter away, to physically remove the surface and have a look at what's underneath the surface. That's called depth profiling, or argon ion sputtering, argon bombardment as they call it here. Very, very widely used. So let's have a look at what happens here. So as we can see here in the supporting information, high resolution XPS of Ti2P region showing the effect of argon ion bombardment on the 2p3/2 peak position of titanium 4 plus. Okay, so let's look at the spectra first. So black TiO2 after 5 minutes argon ion bombardment. Interesting. So you now suddenly get a lot of these extra environments down here, low binding energy environments, which will be to do with the reduced forms of titanium. So titanium 3 plus, titanium 2 plus is what they're assigning them as. You can see them here. That may well be correct. But you get a lot more of that with black TiO2 than you do with white TiO2. So after in white TiO2, after argon ion bombardment, you do get some titanium 3 plus. That's actually pretty well known for TiO2. You do get a lot of, if you sputter it in vacuum, which is what they're doing here, you do reduce it a lot. You get a lot of reduction of titanium. Titanium 4 to 3 or 2, or even metal eventually if you hit it hard enough. So it's not surprising that you see this, but it is interesting that the black TiO2 under what I guess are the same conditions, 5 minutes of argon ion bombardment, you get a lot more titanium 3 plus 1, you get a lot more reduction of titanium. So maybe that's because you have this disordered region at the surface. They're showing, they're showing the amounts. Okay, they're showing graphically the amounts of the of each of the different oxidation states of TiO2 so before argon sputtering, after sputtering. Okay. Note that high energy argon bombardment can also reduce titanium 4. Yeah, that's what I just told you guys. Importantly, in the case of black TiO2, the increased amount of titanium 3 was detected after bombardment compared to white TiO2, but also the presence of TiO2 could be identified after identical bombardment conditions. Okay, so they're doing more reduction. So black TiO2 is easier to reduce with argon ion bombardment compared to white TiO2. So this signals that black TiO2 is either inherently contains more Ti3 Ti2 sites beneath the surface, or that it's more susceptible to bombardment. Okay, I actually quite like this approach. I like the fact that they've done it a couple of times now. They've kind of made an observation and then given different possibilities about what it could be. I actually think that's pretty effective. I think it's effective here. I think those probably are the two main reasons. I don't really see how else that could happen unless there's a difference in our argon ion bombardment, but we can believe they did the experiment carefully, so there hopefully won't be. Notably, electron paramagnetic resonance measurements on black TiO2 material synthesized under similar conditions, so strong paramagnetic signal which can be attributed to formation of Ti3 centers. Okay, so I guess they don't say it outright, but I guess that supports kind of conclusion 1, that the Ti3 plus is there, but it's just hidden underneath an oxidized layer. Now the problem with that is that the XPS is surface sensitive, but it's not that surface sensitive. I mean, you're still going to look about 4 to 5 nanometers, maybe even further into the material. Now remember, we're talking about a particle which is only 25 nanometers in size, so the outer 5 nanometers of that is quite a large proportion of the nanoparticle volume. You're looking at quite a large part of the nanoparticle with XPS. So the idea that maybe underneath, maybe there's an oxidized layer, and then somewhere deep inside the nanoparticle there's some Ti3 plus, which is only then revealed by argon sputtering. It would have to be quite far inside, because otherwise you'd be able to detect it with XPS. So kind of still a little bit puzzling about exactly, is there Ti3 plus here after hydrogen doping, or is there not? Is it only generated by the argon ion bombardment? Anyway, they kind of switched tack quite abruptly now. To determine the position and electron density of the valence band, helium-1 UPS measurements were performed on white and black electrodes, figure S6. Okay, we're jumping back to the supplementary information again, and here we can see the ultraviolet photoemission spectrum, so UPS. So this is another way to try to understand the outermost electrons of the material. So here they're actually using a method to work out what's called the work function of the material. They're using looking at these two cutoffs. So a low kinetic energy cutoff, high binding energy cutoff, and a low binding energy, high kinetic energy cutoff. at the valence band edge. So by measuring these two cutoffs and by measuring the difference between them, and by comparing that to the photon energy which they use, which they know, it's 21.1 electron volts, they're able to work out the work function. So this is a nice way to measure directly the work function of a surface. So are their numbers any different? They're pretty similar, aren't they? They're pretty similar. 2.76, 2.75, and then 16.72, 16.69. So you're talking about tens of milli-electron volts difference there in the work function. It's probably not any kind of real difference you can measure. I'm sure they're gonna, gave similar values for the work function. They're talking about that is. So they're talking about the absolute position of the valence band edge, which is to do with the work function. They measure those as being 0.02, so 20 milli-electron volts different, pretty much unchanged, I would say. So they do then go on to model the, which is actually quite far down. Is it quite far down? Oh no, it's actually, sorry, it was above where I was looking, that's why. Here it is. So it's in figure 2. The background subtracted and deconvoluted helium-1 UPS for white and black TiO2. So here is kind of a similar figure to what was shown in the supporting information a minute ago, except what they've now done is subtracted a background. So a big problem with photo emission in general, but especially for helium-1 photo emission, is that you have a lot of other contributions to the spectrum that are not elastic photo emission from your occupied orbitals. So in normal XPS you have inelastic scattering. You have processes where electrons can lose energy while they're being photoionized, while they're being removed from the material, and that means that they you end up with a high binding energy background on your spectrum. What we have in UPS, especially helium-1 UPS, which is very low photon energy, you have a lot of secondary electrons. So secondary electrons are electrons which are not ionized by the primary photon beam or by the ultraviolet photons coming in. They're ionized by some other energy loss processes. So some energetic electrons have been ionized by the photons, then those electrons bash into another electron which then gets knocked out of its atom. That's a secondary electron. That second electron that comes out is a secondary electron. So you get a lot of, they come up with very, very low kinetic energy, but because the photon energy of UPS is very low, they appear in the UPS spectrum and they can actually dominate the UPS spectrum. So probably you're looking at something like this is probably the background they put on. So probably all of this pretty much is secondary electrons, and then they're looking at this part here. Let's change colour. They're looking at this part here, I think, as being their, looking at this part here, which is their actual photo emission, their actual valence band emission, let's say. Let's call it valence band emission. Their valence band emission. So this kind of wiggly shape here, if you compare what I drew here, is pretty much the same, I think, as the wiggly shape we've got here. So that's basically how they got this. They took their UPS spectrum and they subtracted a background. Now, how did they decide what background to subtract? Well, they used something called a tool guard background, which is one way of doing this, but there's actually lots of other ways of doing it. Tool guard is one of the background functions which is probably most strongly based on some kind of physical phenomenon. Most strongly based on actually thinking about the physics of what's going on there, but it's still difficult to do. There's lots about the background, especially the second electron background that comes out, which is to do with things that are very hard to control, things like the morphology of the surface, the curvature of the surface, the roughness of the surface. These are things which are difficult to control. They can make a good case that they're very similar in these samples, but in general they're hard to control. So they're hard to actually put into a background model with any kind of certainty. You basically have to just fit empirically the background function to the spectrum you see, and kind of hope that you can pull out separately some actual genuine kind of photo emission from the material that you're interested in. But that's what they've done there. It's challenging to do, but that's what they've done. So this kind of wiggly line here is I'm pretty sure, the kind of wiggly, the red part that I drew here, so the background subtracted. What they've then done, and I'm probably going to go ahead and say I don't really agree with this analysis. What they've then done is put a whole load of different components in there to model this spectrum. So this is often seen, I'm not saying this is the case here, this is often seen from people who do a lot of XPS core line fitting, and they use basically the same approach for XPS core line fitting, and they apply that to a valence band. Now in a core line you can model the core line with these Gaussian Lorentzian functions, which is what these things are, which are a kind of a combination of two mathematical functions, the Gaussian and the Lorentzian, and they're there to simulate different kind of physical processes in a core line. So for example, let's go back to the core line. Sorry, I didn't tell you what I meant by core line. This is what I mean by core line, these titanium 2p. Yeah, these things we looked at earlier. These are core lines, they come from 2p orbitals deep inside the atom. They essentially can be assumed to be an atomic orbital. Yeah, they don't really see the outside world. So you know they can be estimated to be an atomic orbital. So as you can see, in fact you can see here, the shape of these is pretty much very similar to the shape that you see modelled here. Yeah, each of these kind of modelled peaks that they're put on there. There's a good reason for that, because the shape here can be modelled, understood as a Gaussian Lorentzian peak, and they've used a Gaussian Lorentzian peak here. So they're using kind of the methodology that people use for a core line, but applying it to the valence band. So they're adding in these kind of peaks here, but the valence band is very different to the core line. The valence band is not an atomic orbital in the same way that a core line is an atomic orbital. The valence band is a combination of different orbitals from different atoms that are interacting with each other. That's why they're the valence orbitals. The valence is the outermost orbitals of the atoms, which are interacting with each other. That's what chemistry is. That's what the bonds are. Yeah. So to kind of treat the valence orbitals, the outermost orbitals, the same way as a core line in terms of this modelling, let's say it can have some pitfalls. It can have some pitfalls. So that may not be what they've done here, but they've definitely taken the approach of adding in these Gaussian Lorentzian peaks. You kind of have to ask, what is the reason for fitting Gaussian Lorentzian peaks to, or this number of Gaussian Lorentzian peaks to the valence band? You know, why have they decided to fit 1, 2, 3, 4, 5? You know, why not fit 6? Why not fit 4? Why not fit 1 million? These are questions which I think are difficult to answer for valence bands. They're easier to answer for core lines. You can make arguments in core lines about, well, I'm fitting this number of peaks because this is the number of chemical environments I expect for this element. You know, so I expect it to have two environments, so I'm fitting 2 peaks. But those kind of arguments don't really work for valence bands. Yeah, it doesn't make sense. But let's see what they talk about anyway. Sorry, we're I think down here. Yeah, okay, so let's find where we were in the text. So the background subtracted UPS spectra, so that's what I spent probably about 15 minutes explaining what happened. But that's these things up here anyway. That's these spectra here. The background subtracted UPS spectra were deconvoluted into 5 components. This is in line with the results from density functional theory DFT calculation. Okay, I might not have time. I might look up this paper and see what it said. I'm pretty sure the DFT paper is not going to say there are 5 components in this valence band, because that's not language DFT people speak. They like to talk about partial densities of states. I don't think they're going to say there's 5 things. But anyway, maybe they will. Maybe they will. The state of highest binding energy corresponds to surface OH species, which has a greater contribution in the case of black TiO2. Component 1 is surface OH species. Okay. So that's this thing here, apparently, surface OH species. Fine. The following 3, 2 to 4, are attributed to hybridized titanium 2p and oxygen 2p. Okay, I think this is probably a typo. I think they probably mean titanium 3p. So titanium 2p is a core orbital. In fact, they even showed spectra from titanium 2p. So I think they mean titanium 3p. while the state at position 5 at the lowest binding energy corresponds to electron density related to surface defects. Importantly, the area of state 5 is 3 times larger in the case of black TiO2 compared to white TiO2. Okay, let's go have a little look. So they're talking about this. Okay, they're talking about this green thing here. Okay, as being surface defect states. So, what do surface defect states mean? I think it's certainly at the moment it's not very well defined what they actually mean by surface defect states. But on the surface, on the face of it, it does look like there is a greater contribution here from the or a greater spectral density here. Let's say spectral intensity here in the black TiO2 compared to white TiO2. That's one of the differences you would say between it. Now, I would be interested in seeing how much of that could be explained by the way that they did the subtraction. So let me rub out. Oh, no, that's the wrong one. Let me rub out my scrawlings and look at the actual data here. So they've subtracted. So this is actually the white here, and this is the black. Okay, so they've put a function along here which they don't show us to subtract the background, and that's how they've got this. Now, choices they make about the function may well influence the size of that component there. And as I said, I don't think there is a kind of strongly a method strongly rooted in physics for how you define that background, because, as I said, it depends on things like the morphology of the surface, the surface area, the roughness, things that you just can't really know for samples like this. If you had a perfectly flat sample, if you had a completely flat crystal surface, maybe you could do, okay, but I don't think you can with these nanomaterials, or at least it's very difficult to do that. So how much does the way that this background is defined influence the shape that you get here? It might do. It might actually. I think probably there is something in it. I think there is something more here in this region. Let me get a pen. Let's zoom in a little bit. Let's get up close with these spectra, shall we? I think maybe there's a little more something here. Oops, a little more something here than in this case. So it's hard to navigate around so well. Then in this case here, then here. Maybe there is, but it's kind of a difficult one. In any case, they definitely think there is, and they think there's more, and they're assigning this to kind of surface defects. This could also be titanium 3+. So for sure, this could be some kind of filled d orbital that arising from titanium 3+. But let's continue anyway, because we're making slow progress at the moment. So. Furthermore, no features related to Ti3+ 3D states from either oxygen vacancy or Ti3+ interstitials can be observed, which should be located between 0 and 2. Okay, well they're kind of contradicting me. They may well be right there. So nothing between 0 and 2. Well, there is this kind of thing here, but they've kind of assigned all this intensity to this component just above 2. But there is something there. So I don't think it's completely definite that it's definitely not Ti3+, but combine it with the XPS results, which didn't detect any Ti3. Maybe that comes out making some sense. It also points towards a disordered crystalline core structure where the Ti3+ moieties are located in the crystalline core, residing below the information depth in both XPS and UPS. This is not surprising because the exposure of the as-synthesized black TiO2 samples to oxygen after the synthesis, even at room temperature, can convert the outermost layers to stoichiometric TiO2, leaving a disordered structure behind. Okay, that's interesting. So they're saying that, okay, they're definitely on the conclusion that the Ti3+ is there, it's what's causing the visible light absorption, but it's buried underneath the information depth of TiO2, so it's buried of XPS, sorry. So it's buried too deep for the XPS to actually be able to detect. Now, as I said before, that means it's probably 5 nanometers-ish inside the material. So you've got a 5 nanometer kind of disordered layer with no Ti3+ or very low amounts, and then deeper inside you have a much higher amount of Ti3+, which you can kind of access through argon sputtering, or detect through electron paramagnetic resonance, or detect with, or sorry, not detect with the UPS. Sorry, the UPS doesn't detect it. So that's their kind of hypothesis, and they say that, well, the reason that happens is because once you take the samples out of the furnace, into air, then the surface becomes oxidized just by reaction with oxygen. The surface Ti3 plus becomes oxidized. So that's interesting, because I'm pretty sure that we ran out of music again. Let's go for this. I'm pretty sure that the if you take Ti2O3, so titanium 3 plus oxide, and handle it in air and measure XPS, you will definitely see Ti3 plus. I'm sure I've done this experiment. I know I've done this experiment. You will definitely see Ti3 plus. So it certainly isn't the case that Ti2O3 will be fully oxidized, in the outermost 5 nanometers just by exposure to air at room temperature. So I'd kind of be surprised if this material is as well. You could argue, well, maybe it's got a higher surface area, maybe the surface is more reactive for some reason. Yeah, maybe it is. Maybe it's got hydrogen in there, that somehow helps. Maybe it is. The obvious experiment you could do, if you wanted to test this, do the whole thing in a glove box. So don't expose it to oxygen, don't expose it to air after the synthesis. Do the experiment in a glove box, or transfer it after the experiment into a glove box without exposure to air. You could put some seals on the end of the tube furnace, probably possible to do that. Get it in a glove box, then load it into the XPS from the glove box, see whether you see any Ti3 plus. That would kind of test that hypothesis, I think. But yeah, I'm a little skeptical about it. This lattice disorder can also result in the formation of surface defects instead of forming discrete energy levels, as the case of Ti3 plus states, which results in a continuum electron density starting from the VB edge up to the conduction band edge, band tail states. Okay, so this is absolutely what they were talking about in the original paper here. The original black TiO2 paper, they talk about these kind of, not these discrete states, which is actually what you tend to see in going back to right at the beginning of the stream, the nitrogen doped TiO2, but these kind of continuum states. That could be advantageous, that could not be advantageous, depending on kind of the application. But I think it definitely kind of agrees with what was previously observed. Okay, so to visualize, the observed tailing on the UPS spectrum can be a sign of the disordered structure of the black TiO2. Previous studies also confirmed the presence of disordered shell by high resolution TM measurements. We've seen that several times on this stream, I'm not going to go back to it. To visualize the difference between surface defects and Ti3 plus states, the UPS of black TiO2 was recorded before and after argon bombardment, figure 2C, with the emergence of Ti3 upon the bombardment. See also figure S5, as a well-defined state arises within the band gap at 0.78. Okay, let's have a look at that. Figure 2C. Figure 4. Figure 2C. Okay, here we go. So it's not maybe not super obvious. Let me zoom in and scoot across here. Okay. Sorry, let's get it on the screen for you guys. There we go. So UPS. Let's get my pen rather than a marker. So UPS of the original black TiO2, and then after argon ion sputtering. So they're using this argon ion sputtering. It's interesting to use. I think I was originally kind of skeptical that you're just forming Ti3 plus through the argon ion etching. In fact, I'm a little bit skeptical about that still. What I would have liked to see here, so their argument is after the argon ion sputtering, you get this Ti3 plus environment down here, which has emerged. But the thing is, even when you sputter white TiO2, you get Ti3 plus. They showed that in their XPS. Yeah, they showed that back here in their supplementary information. So here they showed even when you sputter. Let me get it on the screen. Even when you sputter white TiO2, you still get Ti3 plus. So black TiO2, I agree, you get more, but I don't think it's necessarily proving that this Ti3 plus is from an underlayer, because you'd expect TiO3 plus to form anyway. You saw that in the XPS. So the fact they see the TiO3 plus here, yeah, definitely interesting. Add some maybe weight to their argument, but I still don't think it's completely certain that this kind of core shell morphology, the titanium 3 plus center, disordered TiO2 or titanium 4 plus outer shell is kind of definitely what we have. Okay, we're going to press a little bit further. I don't think we're going to get the whole paper done because I've spent a long time already just on what we've got to so far. But let's continue a little bit further. So let me get my highlighter, my trusty highlighter back, and scroll down a little bit further. Right. So where were we? We were down here. Yeah. So this mid band gap state that they identified in UPS, attributed to titanium 3 plus. I can definitely believe that. But would it be there anyway? Is it definitely indicative of this kind of core shell? Anyway, so we're moving on to photoelectrochemistry now. So maybe that is the time to kind of pause, and we will. I'll sum up a little bit of what we've seen so far on the structural side, and I think it may be we need to talk a little bit about the photoelectrochemistry, because there's some detailed stuff there in another stream. But maybe some other things to highlight. They do some Raman down here. So Raman spectroscopy, we mentioned earlier on, is a vibrational spectroscopy. It tells you about, can give you information on the crystal structure, so complementary to powder XRD. They saw, I think, very limited changes in the Raman spectrum. This is during the electrochemistry, so this is some stuff we haven't been through so far, and maybe we'll leave to next stream. I think the electrochemistry experiments that come up are pretty interesting, and they're nice to kind of see a slightly different approach. But I think what we've seen so far really highlights, and I have been a little critical of some parts of this, and I think that's part of reading a journal article. You try to find things that maybe you think there's opportunities there to improve upon in future. So that's kind of how science works. So I don't so much apologize for being critical of it. I think that's part of the process. But at the same time, what's trying to be accomplished here is very, very difficult in terms of the structural characterization. So understanding what is going on on the surface of a nanoparticle is a very difficult problem. Certainly through experimental techniques, is a very difficult problem. And I've maybe highlighted or given some examples here in this paper about why it's so difficult to do that. So a lot of the techniques that we use that are very powerful in materials chemistry, in condensed matter physics, in inorganic chemistry, for example, powder X-ray diffraction or X-ray diffraction in general, diffraction techniques, are very, very powerful for showing us, as they've done here, for showing us the structure of things. So showing us the kind of atomic scale structure of materials. I'm just trying to find some XRD. I think it is somewhere. It's somewhere in this warning information. Maybe I don't need to show you. Here we go. XRD shows us very nicely what the what the crystal structure is. It can tell us how much of a different crystal structure we have. It can really let us see the atomic arrangement of things. But it doesn't work very well for nanoscale things. It works very well for things which are very crystalline, have large crystal domains. But nanoparticles are not those things. They can be amorphous, they can be very poorly crystalline. And XRD often doesn't give us a massive insight into it. It can tell us some things. So here, they've still got some information out. They've got their annotated root-R ratio, as we mentioned before, through their root-Valt refinement. But will this help us identify a very, very thin disordered surface layer? Not really. It's not crystalline enough. Diffraction can't help that. So what else can we have? We can have XPS, and XPS can tell us a bit about what the chemical environments that are there. So it shows us, we have titanium 4 plus or titanium 3 plus. Again, that's helpful. It doesn't necessarily tell us as much information as we would like. So for example, here they had to argonine etch the material to get through to what they think is the underlying Ti3+. But the very process of argon ion etching causes titanium 3 plus to be formed. So that's another difficulty. By doing the measurement, by actually doing the experiment, you can be influencing the properties that you actually want to measure. It's a difficult conundrum. Other approaches to surfaces that work very well tend to work much better on very well defined surfaces. So single crystal surfaces, very flat surfaces, techniques like scanning probe microscopy, where you can kind of feel the surface. You have a very small probe which kind of runs over the surface and feels what the contours are. Things like atomic force microscopy work very well on a flat surface. Scanning tunneling microscopy, the same kind of thing. Surface diffraction kind of only works when you have a very ordered surface, so where you have a single crystal surface. So options for understanding surfaces of nanoparticles are actually much more limited, and I think maybe that is part of the reason why black TiO2, even after 10 years of research into it and very intensive research, a lot of papers, a lot of people working on this, we're still left with the question of what is black TiO2, and we still have papers coming out 10 years later talking about the mystery of black TiO2. It's still a mystery even after all these years, because nanoparticles, surfaces of nanoparticles, are very difficult things to kind of characterize. There's a lot of the techniques that work well for crystalline materials, or surface techniques that work well for non-nanomaterials. Combining those two together doesn't necessarily work so well because of the kind of unique challenges to nanoparticles. So we've been through about half of the paper. I think I'm going to bring Tuesday's Journal Club to a close. We've been going for a little while, and I've been off on a few different tangents, but hopefully some of that stuff was interesting for you guys. Like I say, my hope is to kind of grow the channel to the point where these sessions can be a lot more interactive. So if you're kind of annoyed by how much I'm talking or how much I'm giving my own views, by all means show up to a stream and start interacting, start chatting, tell me your opinions on these things, or tell me where I make mistakes about things, or give me your opinions on the merits or otherwise of the different papers we're looking at. Follow us on Twitter if you want to suggest papers to review. I'm very happy to do that. If you have published a paper and you want me to have a look at it, yeah, by all means, happy to do that. If you want to even come on stream and discuss with me, either on chat or even if you want to appear on video, that's fine as well. Just get in touch and we can probably sort something out there. So I'm going to bring today's stream to a close. Thanks very much for joining me today. We may finish this paper off on a future stream, but for now, check it out yourselves. !paper if you haven't already. We'll give you the link in the chat. It's an open access paper. You can read the whole thing yourself, and you can come to your own opinions, and I'd be really happy to hear what you guys think about it. But for now, we will bring the stream to an end. Thanks so much for joining us. Thanks a lot for coming along. And if you missed the stream, it will be available for about 14 days, I think 2 weeks on the Twitch channel, but it will also be uploaded onto the YouTube channel, where it will be available forever and ever. For all of your, however many times you want to rewatch, you can always trust YouTube. So it will be on YouTube. It will be available for a while as a VOD on the Twitch channel. Thanks very much, guys, for coming. Great to see you all. Any comments, stick them in the chat. Hit me up hit Journal Club up on Twitter. You can follow me on Twitter as well. You know what my name is, it's written on the screen. You can use Google. You can find me on Twitter. Follow me on Twitter. But more importantly, follow Journal Club on Twitter. Suggestions for future articles are always very welcome. Alright, thanks guys. Thanks for being part of the stream. Take it easy, and I will see you next time.